Okay, this one looks a little bit tricky, but let's give it a shot. I'm just asking you to find the circumference. Actually, I should have asked perimeter. Find the distance around the whole thing. So the first thing we have up here is we have this half circle. Having the center marked indicates that that's a half circle. So how do we find the distance around that half circle? Well, if it were a full circle, how would we find the distance around it? Yeah, circumference is not diameter times pi, right? Diameter times pi, or pi times diameter. What's the diameter here? Well, 3 foot 5 inches times 2, there you go. 2 times 5 is 10 inches. 2 times 3 is 6 feet. So 6 foot 10. Now to do anything with that, to multiply that times pi, we're going to have to convert it just into inches. So 6 times 12 is 72, plus 10 is 82 inches. So back to our circumference, it's 82 inches, times, we'll just use 3.14 for pi. $257.48. Am I done with that for now? No, what do I have to do? Divide by 2 because it's only half a circle. 128.74. So that's from here around to here. Now I've got 3 foot 8 on both sides. So I have to figure out what that is. The easiest if I convert it into inches first. So 3 feet, 3 times 12 is 36 plus 8 is 44. So 44 times 2 is 88. So I'm going to add 88 to that. So 216.74 inches. I've now included these pieces. This is 4 foot 8 across here. Make that into inches. 4 times 12 is 48 plus 8. 56. I'm going to add 56 to that. So 272.74. And now all I have left are these 2 quarter circles. So I'm going to bring them together and make one half circle, make our life a little bit easier. But of course, we're going to have to find the circumference of the whole circle, aren't we? To do that, I need to know its diameter across here. Pretend that looks like a half circle. Yeah, 6 foot 10 was the whole way across. There you go, minus 4 foot 8. So 10 minus 8 is 2 inches. 6 minus 4 is 2 feet. And now to find that circumference, I'm going to change that into inches. So 2 times 12 is 24. Plus 2 is 26 inches. So that circumference will be 26 times pi. And then so 81.64. But again, between the 2 quarter circles, we only have half a circle, so I'm going to divide that by 2, which will give me 40.82. So 313.56 inches is the distance around. How many? Anybody have that? Anybody on their way there just ran out of time? So in some shapes like that that look relatively complex aren't bad. And the other thing about them is because the radius and diameters of half circles and radius of quarter circles or whatever, a lot of dimensions that it looks like we don't have are actually there because they have to be constant. That radius of 3 foot 5 for this piece up top, for example, Well, it's 3'5" here, 3'5" here, 3'5" there. Has to stay the same. Okay, well, we did an example a couple of classes ago, a couple hours of class ago, where we had two measurements that we multiplied. So something like, 5 foot 9 inches times 4 foot 6 inches. And we said that when we multiplied two measurements, we didn't use dual units. We had to get them all into the same unit. So we either change them all into inches or all into feet. If I wanted to convert them all into inches, in fact, I'm going to have you guys do that in your notes right now. Convert them all into inches and multiply it out, then convert them all into feet and multiply it out. See if you guys remember. Okay, so converting it all into inches. 5 foot 9 is how many inches? 69. 4 foot 6? 54. 69 times 54 is 2,726. Of course, inches times inches is inches squared. If I wanted to change those both into feet, what would I do? Was this 5 and 9/12? Is it 9 inches? It's just over 12 because there's 12 inches in a foot. So that's 5 3/4, 5.75 we're going to write it as. 4 foot 6 is 4 6/12, which is 4.5. So 5.75 times 4.5 gives 25.875. Well, that's the question we're going to address right now. To get from inches to feet, normally you divide by 12. Or to go from feet to inches, normally you divide by 12. But right now, this isn't feet and inches. It's square feet and square inches. So if I had 25.875 feet squared, if I put that over 1 and I go to multiply, I put feet on bottom, inches on top, 1 foot is 12 inches. Is this going to actually cancel out and work? Well, first of all, if I did 25 times 12, I get 300 something. Well, see, there's what I was getting at. This is feet squared, not feet. Feet squared means feet times feet, right? So technically, doing my cross canceling, this feet only cancels out one of those feet. So like Adam said, technically we would have to do it twice. So it cancels out both of the feet. And now we have inches times inches makes square inches. And if we look at that, 25.875 times 12 and times another 12 does give us our 3,726 square inches. So what's really happening there? Well, this is one way of looking at it, is just what we did right here, saying, hey, since that feet squared is feet times feet, we have to do the conversion twice. We have to multiply by 12 twice. That makes perfect sense. Another way you could look at it is just like this. 1 square foot is defined to be 1 foot by 1 foot. Well, 1 foot is 12 inches, so that's 12 inches by 12 inches. If I'm looking at area, 12 inches by 12 inches, 12 times 12 is 144 square inches. So 1 square foot is 144 square inches because it's 12 by 12. And again, you can think of it like this. Since it's squared, you have to do the conversion factor twice. So now with that in mind, if I give you 1 square yard, how many square feet do you think that's going to be? Well, 1 yard is how many feet? 3 feet. And you may hear the term linear yard. All that means is a regular yard. Okay? 1 linear yard is 3 linear feet. 1 yard is 3 feet. But this is squared. So how many square feet do you think are going to be in 1 square yard? 9, exactly. 1 yard, 1 square yard is 1 yard by 1 yard, which is 3 feet by 3 feet. And 3 times 3 makes 9 square feet in 1 square yard. Or you could go through the process like we did up there and just multiplying by the conversion factor of 3 twice because it's squared. So convert in your notes for me. (3,456) square inches into square feet. 567 square feet into square yards. Normally going from inches to feet, we would divide by 12. So this is square inches to square feet. So we're going to divide by what? 144, 12 squared. That comes out to be 24. How many of you got 24 out of that? Anybody have any questions as to how that come from? Where that come from? A bit confused, Austin.
Me?
Yeah.
No, it's squared.
Okay. Okay, just making sure. So now we've got 567 square feet into square yards. Normally to get from feet to yards, we would divide by 3, but since it's squared, we're going to divide by 9. What do we get? 63? Perfect. How have you had 63 square yards? Okay. Yep, we're going from a small unit to a large unit. The unit's getting bigger, so the number gets smaller, so that tells us we have to divide. Or we could set it up like this. Put inches squared on bottom, feet squared on top, so that the inches squared will cancel out. 1 foot is 144 inches squared. So that's telling us we have to divide because the 144 is on bottom. There is a unit of area that comes into play that we have not seen before. 1 acre. Now in machining, it's not that important of a unit, but like I said before, construction class takes this same math class. 1 acre, 42,560 square feet. So if I have a piece of land, it's 240 feet by 420 feet. In your notes quick, see if you can tell me how many acres that is. So we're going to find an area, 240 feet by 420 feet. It's going to give us what? 100,800? That's square feet. Since we're not familiar with acres, we're going to do this one out the long way. So 100,800, put it over 1. We'll put square feet on bottom, acres on top. 1 acre is 43,560 square feet. So we're going to take that 100,800 divided by 43,560. 2.314 acres. Not so bad? Well then let's look at the metric system. Recall your units and suffixes from the metric system. Should look like this. Little conversion chart. If I want to convert excuse me, 0.52 meters into centimeters. From meters to centimeters is 2 spots to the right. I move my decimal point 2 spots to the right. That's 52 centimeters. But what if instead of 0.52 meters, we have 0.52 meters squared? Converting it to centimeters squared. Now, from what we saw with our standard units, there's one of two ways we can handle this. We could either just move it twice, because we had to do the conversion twice, or we can look at this and say, each spot on the chart here is multiplying or dividing by 10, right? When I square it, what's 10 squared? 100. So when we're dealing with square units, each spot on the chart is multiplying or dividing by 100. When you multiply or divide by 100, you move the decimal point 2 places instead of 1. Either way you think of it, every spot you move on the chart means the decimal point has to move how far? 2 spots, right? So if we're going 2 spots to the right on the chart, when it's squared units, the decimal point has to move 4. So fill in zeros. That's 5,200 centimeters squared. If we were to continue with that, what if you throw in meters cubed? Well, now what's 10 cubed is 1,000. So each spot is multiplying or dividing by 1,000 or moving the decimal point 3 spots. Or we could say you have to do the conversion 3 times. Either way, every spot on the chart means the decimal point has to move 3 times. So moving 2 spots to the right on the chart, the decimal point has to move 6. 1, 2, 3, 4, 5, 6. We've got to add 4 zeros in there. Get 520,000 centimeters cubed. So we might have (720 millimeters squared going into centimeters squared. From millimeters to centimeters, how far are we moving? From millimeters to centimeters. 1 spot to the left. It's squared, so we've got to move the decimal point twice as far, 2 spots to the left. So that's 7.2 centimeters squared. (0.31 meters squared going into millimeters squared. Now to get from meters to millimeters, it's 1, 2, 3 spots to the right on the chart. How far does the decimal point have to go? 6. Has to go twice as far. It's squared. So 1, 2, filling in zeros, 3, 4, 5, 6. 310,000 millimeters squared. Or we might have .74 centimeters cubed into millimeters cubed. Centimeters to millimeters is 1 spot on the right on the chart. How far do we have to go? It's not going to be double, it's going to be triple this time because it's cubed. So 3, 1, 2, 3, add a 0. 740. Make sense? So the metric system is actually pretty simple. It's just however many spots you move on the chart, you're basically multiplying it by whatever power is on your units. The standard system's a little bit tougher. You have to make sure you square the conversion factor. Or when we talk about volumes, They'll be cubing the conversion factor. We'll talk about that a little bit more in a couple of days. For right now, let's look a little bit closer at these areas. Let's look at rectangles. We started a conversation on geometry a little bit a few weeks back, and how all the geometry is based off of the simplest geometric figure, that right there. It's called a point. And a point is just a location. Everything in geometry, however, is created from that point. If I take that point and I pull it in a single direction, I've created a line segment. Now, quite often in practice, we refer to this as a line, but a true line goes on forever in both directions. So in practical applications, a true line really isn't plausible. A line segment is generally what we're interested in. Now, the length of that segment, as we said before, is just equal to the distance that we move the point. So length and distance are really equivalent. Now, if I take that line segment that I created and I pull the whole segment in a second direction, if I keep that segment in the original orientation, in other words, parallel to where it started, and I move it perpendicular to the first movement. So the first movement I went side to side. This movement I'm going to go up and down, moving it perpendicular. If you think of dragging a stick across the sand or the dirt, what you're scraping out in the dirt is a rectangle. The size of that rectangle is related to the length of that original segment, that original stick, and the distance you moved it again. That distance is often called a width. I refrain from using length times width for area. I use area as length times the distance. Let me show you why. Because it's not always going to be a width. For example, I could have a rectangle like this, where this is 14 inches and this moved 5 inches. What's its area? Of course, we need to know that that's perpendicular. It's a right angle. What's its area going to be? 14 inches times 5 inches is 70 inches squared, right? But what if I don't pull it straight? What if I have my 14 inches here? Well, let's say this time I take it and I pull it at an angle. Well, this is not 5 inches across here, but let's say that the distance from here to here is still 5 inches. What's its area? Well, if you think of this as being a bunch of little rectangles up here that are stacked up, all I've really done is push those little rectangles off like this, right? Have I changed the area? No, I've just changed how it looks. That area is still 14 inches by 5 inches, equals 70 square inches.
Now those slanted lines could be 20?
Yeah, these could be 20 or whatever, as long as the distance from where this stick started to where it ended is still 5 inches. And distance is always measured at a right angle or perpendicular. In fact, it doesn't even have to move straight. It could do something like this. We could, as long as it stays parallel to where it started, and the distance between where it started and where it stopped is 5 inches, its area is still 70 inches squared. This one and this one, yeah, they should be the same. I tried. Yeah.
What should be the same?
These end lines should be the same, because what's really happening here is we're taking this segment here, and I'm just pulling it like this. Yeah. I can slide, as long as it stays parallel to its original orientation, I can slide it side to side a little bit, and it doesn't affect anything. It's just the distance between where I started and where I stopped. Now I can deal with something like this. How's this area going to be found? Well, if I fill this in here, this is just the original rectangle, isn't it? The area of that rectangle is 14 inches times 5 inches. But that triangle is only half of it. So it's divided by 2. So that's going to be 35 square inches. It does not have to be a right triangle like that. It can be like this. But what we're looking for is what the width of that rectangle would be that contained it. For this to be 5 inches here means it has to be from this point here, the corner that's furthest away from that side, measured at a right angle, has to be 5 inches. That's called the height of the triangle, or sometimes called the altitude of the triangle. And that area is still going to be 14 inches by 5 inches divided by 2, because it's half of the triangle. This is what we call a trapezoid. In a trapezoid, these two sides are parallel, but obviously different lengths. So let's say this is 18 inches and this is 28 inches. Let's say the distance between them is, I'm just going to call it 10 inches. What we can do is this. I can go halfway down this side and chop this off square. If I flip that piece up, it should fill that in. We'll do the same thing here. Go halfway down this side and chop this off square. If I flip that piece up, it should fill that in. I now have a rectangle. Its width is 10 inches. Its length is somewhere between the 18 and the 28. In fact, it's halfway in between. If I take my 18 and my 28 and I average them together, I get that length. So the area for a trapezoid is found by averaging the two bases, and then multiplying that average by the height. So this comes up to be 230 inches squared. Now that's more a traditional trapezoid. This is an untraditional trapezoid here. Still works the same. Let's say this is 6 inches, and this is 20 inches here. And the distance between them is, oh, let's go 20 inches. We're going to find that area by averaging the two bases, 6 plus 20 divided by 2, and multiplying by the height, which is 20. So 6 plus 20 is 26. Divided by 2 is 13. Times 20 is 260 square inches. For circles, area of a circle goes off its radius. It's pi times the radius squared. So if this is a 4-inch radius, it's pi times 4 inches squared, or 4 squared, which means it's going to be pi times 16, which ends up being 50.24 if you use 3.14 inches squared. We'll look at that more over the next couple of days. I know I'm kind of rushing through these formulas right now, but one of our main applications of area is pressure. If you look at like a hydraulic cylinder or even a tank that's got pressurized air or any other pressurized substance in it, pressure, the amount of pressure is equal to force divided by area. Which also means the force exerted, I to rearrange that, the force is equal to the pressure times the area. So what do I mean by that? Well, let's say you have a hydraulic cylinder. That hydraulic cylinder has a 4-inch diameter. And you have a compressor, well, hydraulic pump is capable of producing 120 psi. How much force can that cylinder push with? Well, the area is going to be pi times what? 2 squared, right? Half of the 4 is the diameter, gives me a radius of 2. So 2 squared is going to be 4. So that's, yeah, I know. But I just had to make sure everybody knew how we got to the 4. 12.56 inches squared, and then that's going to be times 120 psi. Pressure times area. So 1,507 pounds of force that hydraulic ram will be capable of producing. So in your homework, there are going to be a couple of questions on pressure. See what you can figure out on them. Otherwise, we'll go over them more tomorrow. I realize I got kind of rushed at the end here. In your little book, it's going to be unit 30, the odds. Some of those, when you're doing the odds, it may refer back to a previous problem, so you may have to go do an even problem to figure one of them out, because it says, you know, given the same thing in problem 18 or whatever. So you may have to go back and do that problem to get to it. In the big book, I believe it's page 249, exercise 8.8-5, and page 250, exercise 8-6. I'll double check those page numbers. So yes, page 249, exercise 8-5, and 250, exercise 8-6.